In this part of the presentation, we're going to discuss expressions for equilibrium constants. That is, how is the equilibrium constant in general written in terms of concentrations of the products and reactants. We're not going to get so much into the actual numbers, how they're used, and how to do calculations. That will be in a subsequent So first of all, we consider a generalized reaction, which is written this way. The capital letters represent chemical formulas. So in this reaction, the capital letters A and B will represent a couple of reactants. The capital letters D and E represent a couple of products. So for example, A might be CH4, B might be O2, D might be CO2, and E might be water. And then the small letters represent the coefficients in a balanced chemical reaction. So the equilibrium constant in general is written as concentrations of the products multiplied together in the numerator divided by concentrations of the reactants in the denominator multiplied together. Each one is raised to the power of the coefficient in the balanced chemical reaction. So for example, D raised to the D power. So if this coefficient is 2, then the concentration of D in the equilibrium constant expression is squared. There's another definition that's commonly used, and that is when the reaction involves gases, we realize that pressures are proportional to concentration, so that the equilibrium constant can be defined in terms of pressures instead of molar concentrations. That is indicated by this subscript here. C represents concentration, so Kc, this symbol here represents the concentration equilibrium constant. P here, Kp, represents the pressure equilibrium expression. We're not going to go too much into detail about this, but just on this next slide, we won't do a lot with this, but we want to say something about the relation between the Kc and Kp, where we can have alternative definitions. In some cases, they're exactly the same. So to look at the difference between them, we look at the familiar ideal gas law, PV equals nRT. Rearranging, dividing by V, we get pressure is N over V times RT. Now, if you think about the units of this, N over V, here, that's moles divided by volume, which is simply molar concentration, or the familiar molarity. And it is molarity when it is our common definition of molarity if V is expressed in liters. So this is moles per liter. So that's what we commonly represent by the brackets. So you put brackets around CH4, that represents moles per liter of CH4. Okay, so here's how pressure is related to molar concentration. And when you consider that for reactants and products, won't fill in the details with you, but the pressure equilibrium constant is equal to the concentration equilibrium constant times RT raised to the delta N power. Now what's delta N? Delta N is the change in the number of moles of gas from the reactant to the product. And if the number of moles of gas is the same on both sides of the reaction, delta N is 0, and then Kp equals Kc. Okay, now that's all we're going to say about that. One or two problems on that, and it's not going to be a big issue. A little bit about what K means, the magnitude of K. So remember, in the ratio, the products are in the the products are in the numerator, the reactants are in the denominator. So if I have a very large value of K, and so it's really a ratio of products to reactants. If I have a very large value of K, that means there's a lot more products at equilibrium than there are reactants. And so that means the equilibrium lies primarily to the right. So when I write the chemical equation, it mostly goes to completion. And that would be expressed by K much greater than 1. Now, much greater than 1 can be really, really large. It can be 10 to the 6th, 10 to the 8th, 10 to the 9th. That's not at all uncommon for equilibrium constants. If, on the other hand, K is much, much less than 1, and it's always greater than 0, but if it's much, much less than 1, say 10 to the minus 6th, 10 to the minus 9, again, not at all unusual. That means in the ratio, the products, the concentrations of the products are very small and the reactants are very large. So that would represent a reaction that hardly goes at all to the right. It mostly stays as reactants. So we say the equilibrium lies to the left in that case. If, on the other hand, K is close to 1, that means the products and reactants are roughly the same in concentration, roughly the same order of magnitude. So if K much greater than 1, the products are favored. If K is much less than 1, reactants are favored. And then if K is pretty close to equal to 1, that means the products and maybe you can think of the reaction going halfway. Okay, a little bit about how equilibrium constants are related to how we write the reaction. You realize that if you have an equilibrium that can go both ways, you could write it either way. So, for example, when N2O4 in this equation, when N2O4 dissociates into two NO2 molecules, that's a reversible reaction. It can go from the left to the right or from the right to the left. Now, when we write it this way, the K is NO2 squared over N2O4, the definition given here. And that has a particular value, 0.212 at 100 degrees C. So 0.212 is less than 1, not greatly less than 1, but less than 1, which means that the reactants are more or less favored. So since the reaction is reversible, we could just turn things around and write this. 2NO2 goes to N2O4. When it's written this way, the equilibrium constant has the N2O4 in the numerator and the NO2 squared in the denominator, and has a different value. It's basically the inverse of this. So 0.212 if I write it the first way, 4.72 if I write it the second way. You realize that either represents the same thing, so what the value of the equilibrium constant is really depends on exactly how we write the reaction, and that's important to keep in mind. Reversing the reaction gives us the inverse equilibrium constant. Okay, now we talked about heterogeneous equilibrium. That's where we have more than one phase. Everything we've mentioned so far has reactants and products may be in aqueous solution or as gases. So when we consider a pure solid or a liquid in equilibrium with a solution or a gas, the amount of that pure solid or liquid does not affect the equilibrium. For that reason, it's not expressed in the equilibrium constant expression. It simply, because its concentration doesn't matter, we simply leave it out of equilibrium expressions. So here's an example. And now this point to make here, I'm sorry, there is a mistake here. This liquid should be gas, so keep that in mind, okay? A point to make here is that this represents water vaporizing. Now you might, at the very beginning we talked about that as being a physical transformation, not a chemical change. But for the purposes of doing this, we're going to treat it just like a chemical reaction. So the equilibrium H2O liquid goes to H2O gas, represents vaporization of water. And that can go, as we learned before, in either direction. It goes from liquid to gas, that is vaporization. Gas to liquid is condensation. So what's the equilibrium constant expression for this? Well, we do products over reactants, and we're going to do pressure. But now the reactant is pure water in the liquid phase. We don't express it in the equilibrium constant expression. So you can, so instead of writing in the denominator some concentration of the liquid, we simply have a 1 in the denominator, and the equilibrium expression, the Kp, is simply the pressure of H2O. And that is simply the vapor pressure. This is exactly what we learned before. This is simply the vapor pressure of water, the pressure of water when I reach equilibrium in the vaporization. Here's another example, decomposition of calcium carbonate, which is a heterogeneous equilibrium. So if I have calcium carbonate and I heat it to a very high temperature, some of it decomposes into calcium oxide, solid, and carbon dioxide gas. So now notice in this expression, here's a pure solid, here's another pure solid. Those are simply not expressed in the equilibrium expression, or to put it another way, where they would appear in the equilibrium expression, we just leave a 1 in there. Again, simply because their concentrations don't matter. And then the result is, in this example, we're using Kc instead of Kp. Kc is just the concentration of CO2. The concentration of calcium oxide is left out, is just replaced by 1. The calcium in the denominator, the calcium carbonate is left out. So again, we leave off things that are pure solids or pure liquids from the equilibrium expression. And if we use pressure, equilibrium constant Kp is PCO2. Next thing we'll consider is ionic reactions. You might recall that in an aqueous solution, if something dissolves in an aqueous solution, it splits into component ions. And each ion separately can affect the equilibrium. And for that reason, each ion separately is written in the equilibrium expression. So here's an example. And this will be an important one, important kind of example. We'll do a lot with this when we get to acids and bases. But here is aqueous HF, okay, something in aqueous solution, dissociates into H+, a hydrogen ion and fluoride ion. Okay, all three of these are present in aqueous solution, and there's an equilibrium that exists between them. So what is Kc for the equilibrium? It's simply the concentration of the hydrogen ion times the concentration of the fluoride ion divided by the concentration of the undissociated HF. And we use this for all reactions involving ions. Here's an example involving a solid. So notice calcium carbonate solid dissociates or partly dissolves into calcium +2, carbonate -2, both in the aqueous phase. Now the difference between these two is in this case, HF, the left-hand side, is in the aqueous phase. In this case, calcium carbonate is in the solid phase, a pure solid. So calcium carbonate dissolves, making calcium ion and carbonate ion. Now you may have heard, and you may know, that we regard calcium carbonate to be an insoluble solid. So how can we say it dissolves? Well, there is, when we're looking at equilibrium, just about any reaction we can write will happen, but maybe to some very small extent. So we don't say it's completely insoluble, say it has a very low solubility. And that will be reflected in the fact that this Kc, the insoluble nature of calcium carbonate, will be reflected by the fact that Kc, if we look up a value for it, is a very small number, indicating that calcium carbonate is relatively insoluble. Here's another example for another insoluble solid. Magnesium hydroxide solid splits into magnesium 2+ and 2 hydroxide ions. Same thing, the solid on the left-hand side of the equation is not expressed, and we write the ions on the right-hand side of the equation. Because we have 2 hydroxides here, the hydroxide concentration is squared in the equilibrium expression. And then the final thing, this isn't mentioned too much in the book in this section, but water in aqueous solutions. Usually water is just a solvent, and it's not expressed, and so it doesn't participate in equilibrium. But occasionally the water is a reactant or a product in a reaction. In dilute solutions, the concentration of water does not appreciably change during the reaction. So it's conventional, again, just like the pure solids and liquids, to leave off water when it's a solvent and it's a dilute solution and it's participating in the reaction. And here's an example. If the reaction involves water, it is omitted, and the example we have is ammonia in the aqueous phase reacts with water. That's our solvent. So this is ammonia dissolved in water, and it partly reacts with water to form the ammonium ion and the hydroxide ion. What's the equilibrium constant expression for this? It's the concentrations of these two products multiplied together, and in the denominator goes the concentration of NH3. The water, because it's a solvent in an aqueous solution, is simply left out of the equilibrium constant expression. So the fact it does not, and that simply reflects the fact that it does not change appreciably during this reaction. And then finally, a little bit about stoichiometry and equilibrium constants. This is similar to what I said earlier about a reaction being written in the reverse direction. What the value of the equilibrium constant can depend on how you balance a reaction. So here's an example. If I do this N2O4 and it splits into 2 NO2 molecules, and I write Kc in the way that I wrote it before. Now, normally we balance an equation with the simplest coefficients, but if for whatever reason we chose to write the equation in this way with 2 N2O4 molecules splitting to make 4 NO2 molecules, the Kc would then involve different powers. And if you look at this, you see that what you have, this is simply the square of the equilibrium constant expression written in the normal way. So the lesson that we want to learn from this is the equilibrium, when you express a value for the equilibrium constant, it has to be associated with a particular way of writing the reaction. So we have to keep that in mind. If we write the reaction a different way, we might have a different value for the equilibrium constant. won't matter in calculations as long as we make sure that we're clear on how the reaction is written that goes along with a particular value of the equilibrium constant.